Welcome to Lesson 1 of Unit 4. We are going to be talking about forces and different types of motion in this unit. And we're going to start with Lesson 1. The essential question for Lesson 1 is, how is an object's motion described? And by the end of this lesson, you should be able to describe the motion of an object in terms of reference points, direction, speed, velocity, and acceleration. Okay, so join me on page 174. All right, I'm on page 174, and I'm looking at the blue heading that says, how is motion described? Okay, what is your current position? Well, position is the location of an object. If you decide to stand up and move around, you will move from one position to a different position. Motion is an object's change in position relative to a reference point. Whenever your position changes, you are in motion. A reference point is a place or object to which another location is compared. When describing position or motion, a reference point is used to make the description clearer. Okay, you guys will often hear me, instead of saying reference point, I will say frame of reference, but it's the same thing. Frame of reference means reference points. Both means the object that you're comparing your motion to. Okay, and if you look at the little ski area, I made some notes about frame of reference, and I also put down here that our most common frame of reference is the Earth's surface. So we sort of, without even thinking about it, tend to compare the motion of objects to the surface of the Earth. All right, let's look at page 175. We're going to talk about the difference between distance and displacement. One way to measure the change in position of an object is to measure the distance that is traveled. If you ride your bike 2 miles to school every day, you ride a total distance of 4 miles. This distance is not necessarily traveled in a straight line. So another way to describe motion is to measure its displacement. Whenever an object changes position, it is displaced by a certain distance. Displacement is the actual straight line distance between a starting point and an ending point. And if you will look at the illustration on page 175, hopefully that'll drive home the point of what they're talking about, distance versus displacement. If you leave home and you drive your car to school, well, you've got to drive around the park, okay? But you wind up at the same spot regardless. You could also maybe ride your bike through the park. Again, you go from home to school, you wind up in the same spot. But let's say a bird, for instance, can fly from your house straight to the school over the park. Okay? So the distance you are from where you started is your displacement. Okay? And the best example of something that's close to just displacement is the bird, because it's basically straight line from the house to the school. But the distance that you traveled depends on the path that you take. Also, another point about displacement. Think about car racers or runners on a track, anything like that, where you may be going around and around the same track. If you're a runner and you run a 400-meter race, that's one lap around the track. You have run 400 meters, that's the distance that you ran, but you finish at the same place that you start, so your displacement is actually 0. Okay, so distance and displacement are related, but they are not the same thing. All right, on the previous pages, we were talking about distance and displacement, but that doesn't tell you how fast you were going, and it doesn't tell you how long it took you to get somewhere. It only tells you where you are versus where you started. So describing speed requires a little bit more than just knowing distance or displacement. When you change your position, you experience motion. Speed is the measure of how quickly distance changes with time, and there is a formula that you will have to know, which is speed equals distance divided by time. The standard unit of measurement for speed is meters per second. A lot of times you'll hear miles per hour or kilometers per hour. Those are other units of speed, but they are not the metric unit for speed. Okay? So speed is how fast an object is moving, and you would calculate speed as distance divided by time. And because it's distance divided by time, you're going to wind up with units of meters over seconds, because meters is a unit of distance and seconds is a unit of time. Same thing if you think about miles per hour. It's miles, which is a unit of distance, divided by hours, which is a unit of time. Okay, in most cases, the speed of an object is not constant, meaning that the speed varies as you take a trip or what have you. For instance, when you ride a bicycle, sometimes your speed increases, sometimes your speed decreases. Average speed describes motion over a period of time. The average speed of a moving object is the total distance traveled divided by the total time of travel. Okay, so there's our formula for average speed, which up to now I've just called speed. Total distance divided by total time. So on number 10, it asks you to do the math. Use the formula to calculate the average speed for an 880 kilometer trip that takes 9 hours. So your average speed, that looks like save, but it's S with a little average beside it. Average speed equals change in distance, the little triangle means the words change in distance divided by change in time. So you say 880 kilometers divided by 9 hours. And you do the math, and your average speed is 97.8 kilometers per hour. Okay. Let's look at page 177. We've talked about average speed, but now we need to talk about something a little bit different, which is instantaneous speed. Instantaneous speed has to do with how fast you're going right at that moment. Okay? So another description of an object's motion is its instantaneous speed. This is the speed of an object at a specific instant in time. For example, when the speedometer of a vehicle reads 88 kilometers per hour, it indicates the speed of the vehicle at that instant. So a speedometer reads instantaneous speed. The reading on the speedometer changes as the speed of the vehicle changes. The instantaneous speed may be very different from the average speed. So for instance, if you are sitting at a stoplight, your speed at that moment, at that instant in time, is 0, but then the stoplight may turn green, you start to accelerate and move faster and faster and faster, and your speedometer will tell you how fast you're going at a particular instant. And let's say you get up to highway speed and you're cruising at 60 miles an hour for a while, and then you pass a car, and you have to speed up a little bit to do that, so your speedometer reading is going to change. Then you have to hit the brakes. Your speedometer reading is going to change a little bit. Okay, your speedometer reading is always telling you how fast are you going at that particular moment in time. Okay, and that's different than average speed. Average speed would be like take your whole trip, the distance for your whole trip, and divide it by the total amount of time it took to get there, and that's how you're going to get average. But a speedometer, you're going to look at is going to tell you the instantaneous speed. Okay. For you guys, there's really no way to calculate instantaneous speed other than reading the speedometer, or later on there might be a trick or two that you can use with a graph. All right. So I'm looking now at the second paragraph on page 177. The changing speed of an object can be displayed on a distance versus time graph. Why am I using distance versus time? Well, if you think about it, speed is distance divided by time. And if you're learning in math that slope equals rise over run, rise would be up and down, which is your y-axis, and run would be side to side, which is your x-axis. So speed equals distance divided by time is really slope equals up and down divided by side to side, rise over run, okay? Because if you look at the graph down in the little yellow section, you notice that your y value is distance and your x value is time. Distance divided by time will give you speed. Okay, use the distance versus time graph. Determine the instantaneous speed of the bicycle at 4 hours. Okay. Well, you can't really determine the instantaneous speed unless You have a nice straight section on the graph, because a nice straight section on the graph tells you that you are going a uniform speed the whole time that that line stays straight. Okay? If you look, we can break this graph basically into 3 sections. It's like 3 little graphs all together. You have the first section where it's over the first 2 hours, and you cover a distance of 20 kilometers in that 2 hours. Well, 20 kilometers divided by 2 hours is 10 kilometers per hour. So for that whole first part of the graph, you're going 10 kilometers per hour. But from time equals 2 to time equals 3.5 hours, you don't change your distance at all. So for an hour and a half, you go 0 kilometers. So your instantaneous speed that whole time is 0 divided by 1.5, which is 0. And then from 3.5 hours to 6 hours, that's 2.5 hours that go by, you cover another 20 kilometers. So what would be your speed that whole entire time? It's 20 kilometers divided by 2.5 hours, and you're going 8 kilometers per hour. Okay? Now, generally, when you look at a a distance versus time graph, first of all, the line is going to represent your speed, but please write this down, and I've written it for you. The steeper the line, the more straight up the line is, the faster the object is moving, because it's covering more distance in a shorter amount of time. Okay, so steeper slopes mean greater speeds. And if I know that, then I can simply glance at the graph without doing any calculations, and I know that the middle section I'm going the slowest. I'm actually stopped because the line is horizontal. The last section is my second fastest section, and then my first section from 0 to 2 hours is when I'm actually moving the fastest, because my line is the steepest at that point. 12 says to explain the relationship between speed and steepness of the slope of the line on the distance versus time graph. Well, I've actually done that for you if you write down what I've asked you to write down. Okay? That should take us through the first several pages of Lesson 1 for Unit 4.